Hello, this is Tony Heller from RealClimateScience.com, setting the record straight about climate. I'm sitting here in my office in Boulder, Colorado, completely powered by natural gas. Our electricity in Boulder comes from burning natural gas. My heat and hot water both come from burning natural gas. It's very cold outside, and without natural gas, I would be freezing in the dark. And the same story for my 120,000 progressive neighbors here in Boulder. I looked at the National Oceanic and Atmospheric Administration climate webpage this morning, and they were prominently bashing natural gas. They said methane is roughly 28 times more efficient at trapping heat in the Earth's atmosphere compared to carbon dioxide, and current levels of methane in the atmosphere are higher than at any point in the past 2,000 years. And here's a graph of methane levels measured at Mauna Loa in Hawaii over the past 30 years. You can see that methane has gone up from 1,700 parts per billion up to about 1,900 parts per billion. Those sound like big numbers, but they're actually very small. To put this in perspective, if everybody in the Rose Bowl represented one molecule of the atmosphere, not a single one of them would be a methane molecule. Or if everybody in Wyoming represented one molecule of the atmosphere, only one person in Wyoming would be methane. Methane is extremely rare in Earth's atmosphere, and a little bit later on I'm going to explain why. In 2009, I was hired by the National Center for Atmospheric Research here in Boulder, Colorado, to find a way to speed up the radiative transfer model. The radiative transfer model is how they calculate the greenhouse effect in their weather and climate models. So I'm very familiar with how these models work and how to use them. Using the standard mid-latitude summer model, I calculated the effects of varying greenhouse gas concentrations. The blue line represents methane, the red line represents water vapor, and the yellow line represents carbon dioxide. The x-axis of this graph is a log scale which goes from close to 0% of current concentrations up to 1,000% of current concentrations. And the y-axis is the amount of downwelling long-wave radiation, which is essentially the greenhouse effect. The red line represents water vapor, and you can see that increasing the amount of water vapor in the atmosphere has a very strong impact on the greenhouse effect. The yellow line represents carbon dioxide. You can see that increasing the amount of carbon dioxide in the atmosphere has some impact on the greenhouse effect, but not nearly as much as water vapor. And the blue line is methane. You can see that increasing the amount of methane in the atmosphere has almost no impact on the greenhouse effect. If the amount of methane in the atmosphere went up to 1,000% of current levels, the impact on the greenhouse effect would be pretty close to zero. Now we're going to look at why methane has so little impact on the greenhouse effect. Each greenhouse gas has a limited spectrum of light which it's able to absorb and re-emit. Across the x-axis of this graph is the wavelength of light, which is essentially the color. However, these wavelengths of light, or colors, are not visible to the human eye. The gray area represents the absorption or emission spectra of each gas. You can see that water vapor has a very broad spectra, meaning that it can trap a wide range of wavelengths of light. The spectra of carbon dioxide is substantial, but it's much less broad than water vapor. And if we go down to methane, we can see that it has very small spectral bands. Methane has very little impact on the greenhouse effect on Earth because it's not very abundant and also because its spectra is very narrow. And something which makes methane even less relevant is the fact that its spectra overlaps with that of water vapor. So if there's water vapor in the atmosphere, the methane essentially becomes invisible. Some places in the solar system have a lot of methane. Saturn's moon Triton is covered with methane oceans, and Pluto has methane dunes. So why does Earth's atmosphere have so little methane? The explanation is very simple. The reason we don't have a lot of methane in our atmosphere is because we do have a lot of oxygen. Methane and oxygen react to release water vapor, carbon dioxide, and energy. That reaction is how we cook, heat our homes, and generate electricity with natural gas. You can't build up a lot of methane in an atmosphere which contains a significant amount of oxygen because it quickly reacts and forms carbon dioxide and water. These claims from NOAA are complete nonsense. They're demonizing our most abundant energy source. And this demonization of methane also allows climate alarmists to attack the meat industry because cattle belch out a lot of methane. Once again, I have to ask, who is behind this disinformation campaign against America's most abundant energy source and against America's farmers? The campaign against methane has nothing to do with science and everything to do with politics and propaganda. Visit Toto on the web at realclimatescience.com. He's been pulling back the curtain on junk science and propaganda for a long time.